Swayam Prabha. Digital India. Educated India.
Good morning, welcome you all to the next class in this particular course on analytical, spectral, microscopy applications of inorganic compounds and nanomaterials. Just in the previous class, I've been talking on the thermal methods, particularly we were going through the TGA and DTG aspects of it. Let us continue with it, and I've already explained in that class the how to understand, how to look at the thermogram and then get the peak points, then the weight losses, their calculation, all of those. Now let us look at continue with that to understand better. If you use for some kind of a mixtures kind of a situation, can we use this? So for example, in earlier I have talked to you about the calcium acetate, calcium oxalate, these kind of things, and then goes through the thermal decompositions. Here I have an example brought, which is a mixture of different oxalates that you can see here. This is nothing but a barium oxalate, strontium oxalate, and calcium oxalate. Any of these salts generally come with a lot of water, so therefore the initial will be the water loss, and the next step will be the once the completely water is gone, then it is the oxalate will start getting broken, or when the oxalate gets broken, it will form the carbonate and then carbon monoxide, and the carbonate again after much higher temperatures again will break down to oxide and the CO2. So this is the common process for all of these in that. So as an example, you can take C2O4 oxalate will give you CO3, and this will give you metal oxide plus CO2. These are the kinds of things that you would see. Okay, so here if you see the mixture, there is one weight loss here which is in lower temperatures 200 to 250 below. There is another weight loss between 400 to 500 range. So the first one within 200 comes from the water loss, and the second one it comes from the breakage, the oxalate into the carbonate and carbon monoxide, and the third one there are two, and of course can be more also, that because here you have a mixture, so one of the carbonate becoming oxide, another carbonate becoming oxide, maybe another becoming oxide. So actually the other one is also overlapping here, so just little beyond that. So if you see individual now from the TGA, it's very difficult to make out individual weight water losses, but if you look at the differential curve, that is your DTG, which is dm by dt or dw by dt, you can see three peaks, 140, 180, 205. So the 140 is for one of them, 180 is for other one, the 205 is. So all of them between 150 to 250, that's where the water loss. The next one is the decomposition of the oxalate. Here you don't see very clearly three, so all of them roughly around 450 decomposing from the you can see very nice straight peaks. That's where you can see the straight derivative curve and not much of the breakups into that. Maybe you can visualize one on this side, one on this side. It's a bit difficult unless you have a much more resolution. You can get that if you change your temperature profile bit slowly. You can also obtain that. Instead of going 10 degree per minute, you can go for 1 degree per minute. Or if you are already going 1 degree per minute, you have to go much lower than that. So if by changing the rate of speed or the temperature variation, you can also resolve that one. The next one is around 780, other is 1030, etc. So these are all happening for the carbonate to oxide, calcium carbonate at 780, strontium carbonate around in this one side, and the other side further beyond 1000 degrees Celsius. So the decompositions occur much higher. Now you know where the water loss, the lower temperature, oxalates break down somewhat intermediate like 400, 500, and then the carbonates go beyond 700, 800, even 1000. So, it's very easy. So, you can easily make out. Now, other thing is, from the area of this you can get the ratio of this. Suppose I have given you unknown mixture of these three, and I have given you a TGA, and then you can always calculate the DTG easily from the differential, and then I ask you to identify the amount of each of these oxalate that I gave you in the beginning. You can get out from this, from the area of this. So, there is absolutely no problem on this. So, this is the TGA thermogram, this is the DTG, and this does not require additional experiment, and this requires experiment. This is just a mathematical thing. Now, I have given carbonates itself. So, if you look at the magnesium carbonate, you can see here the one big loss, great loss. If you take a calcium carbonate, one great one. So, this is happening between 660 to 840, 650 to 850 range, and this is happening a little bit early, around 450 to 550 range. So, around 500 or so. So, they are happening at different temperatures in fact, and the temperature difference is quite far. This is around 750, this is around 500, the difference is 250. That means, if I take a mixture of these two, and even if I go a bit fast in heating rate, still I can separate these two in the thing. So, individual thermograms you can see here, other thermogram. But now, if I take a mixture of these two carbonates, namely the magnesium carbonate and the calcium carbonate mixture, still I can find, see, one of them as the other, because their temperature differences or breakdown temperature differences are something like 200 to 250 degree difference is there. So, it's around 750, this is around 500. So, there is a 200 plus difference is there very nicely. So, you can see this is a mixture. So, you can get one, you can get two. So, from this measurement itself you can estimate how much of the X here is coming from the magnesium carbonate and the Y is coming from the calcium carbonate. You can easily make out. So, a little arithmetic is given here, you can sit and work out. So, this is the thing where you have very simple and easy to get. So, this is a weight loss. So, this weight loss you can get from the experiment, and then from this calculation, this 1 mole of the magnesium carbonate will give you 1 mole of carbon dioxide, 1 mole of magnesium oxide. Same thing is true with all the carbonates. So, therefore, you can easily get the thing, how much of that. So, you can find X, you can find Y in the mixture. I hope that is clear. Same thing is true even in the previous example which I talked to you here also. You can get from here, and if it is not resolved, you can get from here, and you can resolve and find out too. Here it is a little bit of difficulty, but if you go to an experiment where you do it with a slow rate of change of temperature, you can get much better. So, now let us look at another technique. It is called differential thermal analysis. Differential thermal analysis. So, what is that? Is a thermally analyzing, is a differential, means difference. So, difference between what? Difference between a sample and a reference. So, you have a sample, you have a reference. So, these two are put into some chamber and put into a heater. So, both the sample and the reference are heated with the same profile, same kind of a mode of operation, same temperature. So, now you can see that what is the kind of a temperature difference that is coming in the sample when compared to the reference. That is what. So, what you are going to measure? Not the weight loss, not the weight difference, your temperature difference between the reference and the sample. But your heating profile is same for both. You are heating at the same temperature both of them, but one of them will have a difference in the temperature as compared to the other is reference, this is the sample. So, that can be either temperature increasing, temperature decreasing compared to with respect to the reference. So, you have already heard in your early studies the exothermic and endothermic processes. Okay. So, so the temperature difference lowering endothermic, temperature difference is increasing the exothermic. So, that means with respect to reference, your sample is going to be exothermic or endothermic for the same temperature that you use. This heater will give T temperature same to the reference, same to the sample, no difference, but sample's temperature either rises or decreases. This rises because exothermic, it decreases because endothermic process happening in the sample. So, in the sample something is happening, as a result of that this exothermic or endothermic. If nothing happens, then you will not find anything. So, you will not find any change in that. So, that means what you have seen earlier was the weight percentage. Now, what you are seeing, difference in temperature. So, here, so you have in the difference in temperature T, delta T. So, you can have, let us say, positive, you can have negative. So, you know that this is for the temperature is increasing, this is exothermic, and this is for the endothermic. So, sample with respect to your reference, and reference nothing happens, that is what you take. Basically, you take a kind of a reference where no changes occur as a function of temperature. So, whatever occurs is in your sample, and that is what the difference in temperature you are measuring, not the weight difference. So, you plot your delta T versus this one. So, you can see if nothing happens, if both of them are the same, then the change. So, you are using time. Why? Because you are heating the chamber at a particular rate, that is why you are using time, starting temperature and the rate. So, that will give, or you can also use the temperature also. So, on the x axis you can have a temperature, or you can have time, because you have programmed the heating pot. So, heating pot is programmed. So, therefore, that now, so in one case you see this is the initial temperature, this is the final temperature. So, it is going with a blob up, is a positive. So, that is the exothermic, and you see here, and it is going down, the blob is going down as a function of temperature, that means endothermic. So, here the sample temperature is reduced, though you are heating outside, sample temperature is reduced because some process took place. That process is called the endothermic here, that process is called exothermic, and if you apply the background you will get the peak nicely. So, this is with the time, and you apply the background, subtract, and then you will get Ts minus Tr, that is sample minus the reference. Okay, you can take the either way, it does not matter. Conventionally this sample minus reference, you get this one. So, this is for the exothermic, and here you get here for the endothermic. So, you can see that the processes, something is happening in your thing. So, earlier what you have looked at is the weight loss. Now, you are not looking at the weight loss, temperature either gain or decrease, temperature. So, that means temperature of the sample increased, temperature of the sample is decreased. Temperature of the sample is increased when there is a exothermic, and the temperature of the sample is decreased when there is a endothermic. I hope that part is clear, and you can see, suppose you started with the temperature from the sample heating from the room temperature, slowly heating. So, one other thing you can think of, it may melt, another thing it may boil, etc. All of these are requires heat, energy to be supplied. So, therefore, you are getting it as a endothermic processes in these ones. Okay. So, the DTA curve provides the data on the transformation that have been taken place. So, such as glass transition, I will explain you in later stage also. That means going from one state of solid to some kind of a melt state is called the glass transition. Crystallization, going from one glass to crystal, or one crystalline to another crystalline. Melting, the whole substance is melted. Sublimation or boiling, the whole substance is boiled or boiling or subliming. So, these are the things. Now, how do you do? You take each curve and get the area of that, and that area can be used. These are nothing but the enthalpy here. In the previous case, the difference between the two peaks is the weight loss percentage. Here it is the heat. So, enthalpy, the area will come with the enthalpy. So, the delta T versus T. The T could be the time if it is a rate programmed, otherwise temperature, capital T or small t. Now, you can see the same thing whatever I explained to you, and if you do the experiment, I plot as a function of temperature and difference in temperature. Some places not much, kind of a not towards positive, not towards negative, is a little blob, and that is what the glass temperature is. going from solid to some kind of a little liquid kind of thing. When the crystallization takes place from melt, what will happen? Energy is liberates. Why? This is called the energy for the the lattice. When it is formed, energy is released. That is called the lattice energy. So it is exothermic. Then you want to melt, you have to put the energy in. So that means endothermic, you can see. And then you have, suppose you have oxygen, or you are burning, your combustion, then you combine with the air, combine with the oxygen and burn, and then that will be exothermic, you can see. Or decomposition can be endothermic. Okay. So these are the kinds of things. So solid to liquid like material is the glass, and then crystallization, melting, and oxidation, decomposition. Many possible things are there. So the same thing is shown here by one peak, another peak, which is, this is the, if this is a positive side, delta is called exotherm, if the negative side is endotherm. So here exotherm, endotherm, and then this is the some heat capacity change, not with a specific kind of thing. So going from one kind of a state to another state, that can also be measured in this, but that most often measured by another technique, which I will show you later on. So when you have a peak, so you can measure the area, and this area is proportional to the heat, the delta H that is there with that. So that can be compared with one peak to the other peak to the other peak, with one compound to the other compound to the other compound. So you can always, with respect to a standard or reference kind of thing. Okay, here I have a TGA, also I have some DTA of that. First let us look at the TGA of that. TGA of the copper sulfate 5H2O we may have. So there is one loss, another loss, another loss. I think we have already looked at earlier, and you can see, and this going down with the copper sulfate to copper oxide, sulfur dioxide plus O2, and when it is resolved you get it in two peaks. When it is not resolved, you don't see the two peaks, but otherwise it is there. Okay. So anyhow, I have already explained to you in the earlier case where it must have been done with a little lower slower rate of change of the temperature. Now coming to the zinc sulfate here, 7H2O, and here there is a big loss within 100 to 150 degrees Celsius, and then that is correspond to 6 water molecule loss, and then that becomes ZnSO4 1H2O, and here, and this is further loses that, and then by 300 degree it will become just anhydrous zinc sulfate here. Okay. So if you look at the TGA, you see the first step, the 31.8. So what will happen? You take that formula ZnSO4 7H2O, calculate the molecular weight, and then you take for the 6H2O. So the mass of 6H2O by the mass of the total mass magnesium sulfate 7H2O, all this, that will give you the mass ratio. Then you can make the percentage, then you can, or conversely you can take this ratio and convert into, it will correspond to how many water molecules, and then this will be this another loss, another corresponding to that. So these things, so if you look at the DTG curve, this is the DTG curve and this is the DTA curve. So the DTA curve for this one is going down, negative side, delta T negative side is endothermic, and here again going down, and this is also endothermic. There are two endothermic processes within 300 degrees Celsius. So this means water loss in 2 steps. So water loss in 2 steps. So this is the endothermic peak, this is the endothermic peak. This is the DTG curve, there is a differential curve. Okay. From this you can get exactly at what temperature is happening. So this is one temperature, this is another temperature, etc., etc. is happening. So so these are the kinds of things. Okay, suppose DTA, let us look at one of that. It is a differential DTA thermogram. So differential thermogram generally is always shown on the y-axis by delta T. If it is shown with the weight, it is a TGA, that is. So the TGA, DTA you should be able to differentiate too. Now this is the sulfur thermogram. When you look at that, there is one peak over here, another peak here, another peak here, another peak here. Okay. So these are all peaks coming from the different types of sulfur crystalline natures. there are different kinds of sulfur crystalline natures are there, and they all have a different at their melting Tg temperature. Then this melting, and then they will vaporize. They will vaporize at a very high temperature or boil. So the boiling temperature is at a higher, you can differentiate from the melting temperature. So this, okay. So and these are all on what side? Upper side. But upper side here is put as endothermic. But so don't say upper or lower. Always look at which is positive, which is negative. So it's already written here endothermic. So up peak, these are all endothermic. So obviously your melting is an endothermic, the boiling is an endothermic. These are all endothermic. Look at another example, not with the sulfur, the benzoic acid. So this benzoic acid is done at 2 different pressures, okay. So one is done at the curve A is taken at the atmospheric pressure. So you find one around 130, 140 degrees Celsius, another peak around 250 to 60 degrees Celsius, okay. And so that the benzoic acid part of that. And the next one, when you apply the temperature very high, pressure very high, the 200 psi, which is nothing but 13.79 bar, when you apply, this peak is coming at the same, but this particular peak is shifted to a much higher extent, okay. So so that is what is happening. So how do you understand this one? So this is a decomposition of the carboxylic group, and this is some water loss of that, a moisture loss of that, and this is the higher temperature with the carboxylic group breaking down to CO2, and then when you apply the pressure, what happens is that the CO2 which is liberated at the temperature, at this temperature, is pushed back by the pressure that you are applying, therefore there will be an equilibrium, and therefore it will go back to the benzoic acid, will not come to the broken part of it. So therefore you require a higher temperature. So this is happening at 260, let us assume. This is happening around 400. So around another 150 degrees Celsius is increased when you increase the pressure of that. So which is the process? Both the processes are at the endothermic, and the second endothermic process is affected by the pressure. First endothermic process is not affected because there is no equilibrium pushed back, because here whatever the CO2 come at that particular temperature is pushed back to the reactant, and then the reactant will react again. The starting material is pushed with the CO2 that is liberated. So therefore there is a you know that very much Le-Chatelier principle, the equilibrium will be shifted if you have one of the component maximum in one side. So therefore you have the product, one of the CO2 is more and pushing into this direction because of the pressure, okay. So you can do such kind of experiments also using this with the DTA. Yes, so we will look at both the TGA DTA combination of these ones. We have already TGA of the calcium oxalate, calcium acetate, etc. So calcium oxalate, the first one is water loss, the second one is CO, because oxalate breaks down and gives carbonate, and the carbonate breaks down to give oxide. So this we have already seen. Now if you look at the corresponding DTA, that is differential thermal analysis, on this side is put as a positive, so exothermic, this side is put negative, endothermic. So the first process, whatever is happening here, so you can see between 100 and 226. So now you can get exactly correct temperature also from here, from the x-axis, and this is the loss of water. If you want to throw the water out, you need to supply the energy, therefore it is endothermic. Now so this spontaneously breaks down oxalate at that, or carboxylate is also not a wrong thing. So this oxalate, and when the temperature raised to around 225 till about 350, so as you keep increasing the temperature, you will start breaking it, and this is the exothermic process. So that is the calcium carbonate plus the CO. Then the calcium carbonate, what is formed now breaks down to calcium oxide plus carbon dioxide, but this requires energy to be, because that lattice requires to be broken here, because here it happens in the spontaneous way with the temperature. So therefore that process is exothermic and this process is endothermic. So in this particular calcium oxalate, so this becomes from weight losses you can work out, from the temperature variations, that is delta T, you can work out. You can work out direction, whether it is exothermic, endothermic. Therefore you can make the whole thermal analysis plot for this particular thing. Look at the other example, calcium acetate 0.5 H2O thing, and you can see this is the TG thermogram. There is a small bit of things losing slowly with that within about 250, and then there is a great sudden down, and there is not much, then there is a sudden drop of that. So you can see at this the water is coming out, here acetone is coming out. I already explained to you earlier in the previous class, and here CO2 is coming out. So this is the dTg gram, so differential, that is dm by dt kind of thing. So it will tell you if there are more than one peak, etc. So you can see that it comes in two steps. The water loss comes in two steps, it does not come in one step. So similarly the acetone loss goes in the two steps, because there is some intermediate kind of a complexation possibility, that is why you will get two steps, and then the carbonate goes in one step to the oxide. Now let us look at the dTA for this. On this side exothermic, on this side endothermic. So you have in the inert atmosphere, there is no reactive atmosphere, and 14 ml per this, that is the rate at which the inert atmosphere gas is passed through. So it is not very important at all. So you get one peak around between 200 and 300, other peak little above 400, 430, 440, then another peak about 750. So you can see this one is coming from the water loss, this one coming from the acetone loss, this one coming from the carbon dioxide loss, breakdown of that. And now if you use an atmosphere of carbon dioxide instead of atmosphere of argon, so you are putting that. So what you see, you have the first process, second process, slightly affected because of this CO2 pressure, and because CO2 is also involved in the first one to some extent to get back to the starting. That is why you have a movement, because this acetone when it comes, the CO2 would also interact with the other product of the, after the acetone is lost, the other calcium product. So therefore your temperature is moved. But what is moving maximum is this one. What is this one? This is the calcium oxide carbonate breaking down to oxide. So breaking down to oxide gives the CO2. Now you are supplying the CO2, therefore your mass balance moves towards the reactants, from products towards the reactants. So your CO2 is more, so therefore that pushes the reaction to go back. That means you require more energy, more temperature to heat in order to break that one. On the other hand, instead of the argon, instead of CO2, you put the oxygen. So if you put the oxygen, what happens? You are trying to favor the combustion reaction. So you are trying to favor the combustion reaction. Therefore your calcium, this particular process will become more exothermic. So this is in presence of air. In presence of air, this the water is lost. There is no, that is still endothermic. Then is the calcium acetate breakdown. That process is favored in presence of the oxygen because that burns. And the next process of course is the same as the other one, that is the calcium carbonate coming to the calcium oxide plus carbon dioxide. That will be very minimally affected in presence of the oxygen. It will be maximum affected in presence of the CO2. So not affected in presence of the argon. So these are the kinds of things that we have. So we have looked at the two processes, one the TGA and the DTA, and I have put down something taken out from some one of the sources I have given you here, the differences between in the TGA, the weight loss, function of temperature or time, and TGA, the temperature difference. You see the horizontal kind of things, then you see upward and downward kind of things. Okay, so that is where the things are. Okay, so you will find something like that. In the other case, you are seeing like that. So this is for the TGA curve part, this is for the DTA, and this is the weight loss, weight percent, and this is the temperature. So those are the things. It is only for substance which shows change in the mass or heating. DTA does not require a change in the mass, as I told you, but process, what is happening. Is a taking or giving out, those are the things. What is absorbed, what is liberated. Temperatures to break down, use that you can use the upper temperature used for the higher than that of the TGA. So, the quantitative analysis is done from the thermal curve by measuring the mass loss, here by measuring the peak area. The peak area is correspond to the heat of that. So, the data obtained in the TGA is useful for determining purity and composition both, okay, and drying, ignition, etc., all those things is determine the temperature of transition, reaction, melting and boiling, all of those you can work out in this. So, I have a couple of more process. I will be showing some more examples of the things as we go across. It is not that we stop the DTA, TGA now and then make we stop the basic principle, but combining with the examples will continue to happen. Then we have two more techniques and then we will have some more generally where one uses all these kinds of things, techniques, thermal analysis techniques will also come in the next probably it will take another couple of more classes to complete the thermal methods. Thank you very much.